Posterity. Okay, so last time we had talked some about functional abstraction, and particularly talked about the use of abstraction by specification. So I made this distinction between abstraction. So these are types of abstraction, and one of them is by parameterization. And another one was by specification. Now, can anyone remind me when we say abstraction, what do we mean?
Abstraction is like you don't need to think about the entire program all at once. You think about little pieces at a time.
Okay, that's part of it, and that's tightly tied up with this notion of modularity. Only being able to reason about small pieces without worrying about them being connected to everything, and having to think about how everything works in order to improve a component, modify it, write it for the first time, etc. So that's part of it. What else do we mean by abstraction? I emphasized a couple things with it, and I wanted to revisit this because it's a theme that's going to carry with us for 2/3 of the class. So again, what do I mean by abstraction?
Thinking about things in broader terms, so that without worrying about the nitpicky details.
Okay, that's a large part of it too. And your name?
Tom.
Tom. Okay. So if we add Tom's comment to Royce's, we're talking here about hiding details and in treating a lot of things that would individually be considered in a fragmented way, sort of just as totally separate things, is more or less the same, right? So we can have, say, one function to handle 10 different cases just by passing it different arguments, giving it different parameters, right? Instead of having some hard-coded text in a place, some code that tests, is this certain thing equal to this string, or is it equal to this string, or is it equal to that string, or this other string? With the same basic code, we turn it into a function, right? And we pass in the string we want to compare it to, and it does the work to do that. And so we turn many specific cases with all their gnarly details into one common sort of element that we can reuse, right? So reuse has to do with part of it. Okay, so I've talked just now, I've emphasized as an example parameterization. Instead of having all these cases where we compare it to different strings, we turn it into one construct. Maybe it's a function, maybe it's a class that takes care of that job, and we parameterize it. We just pass in, hey, compare it to this time, compare it to this other thing this other time. What is abstraction by specification? How does it figure into this notion of abstraction? So last time we talked, you may remember, about the ways we can use specifications to sort of improve code, and the ways we can make the code clearer by providing these sort of specification. We'll talk about it a little bit, but these specifications have different styles. These ones happen to talk about effects. We'll also look at preconditions and postconditions. But what do these specifications have to do with abstraction?
The idea of creating a contract where the function is expected to do something, but you don't necessarily need to know how it does it.
That's exactly right. We want to be able to think about what it does and not all the gory details of the how, right? It comes back a little bit to Tom's comments and also to Royce's. We want to be able to focus on an area of the program and have confidence about what it does, maybe because we want to make use of it without needing to know all of the gory details, all those gnarly little details about how exactly it does it. And specifications allow us to do that. They allow us to deal with a high-level contract, right? Why is that an aspect of abstraction? So I've just been emphasizing the benefits that offers to us as the users of that abstraction. But how about for the folks who write that abstraction? Why is it, what benefits does it give them?
Clearer goal as to what you're doing.
Okay, clear goal as to what their code has to accomplish, and that's key, right? Often you can write these specifications very early on in design, maybe for the next deliverable of an incrementally delivered project. You create these specifications for this component, it haven't been written yet, but because you've created them, lots of people can get doing their job. The people who are going to create this abstraction can start doing their job, and the people who are going to use it can start doing their job because they know what it will do, right? Both of them have a clear understanding about what's required and you know how and what it does. So that's part of it. But the person who creates that abstraction, why do we say it's an abstraction? Why do I say it's taking lots of what would be totally different cases and creating sort of a common thing that supports all of them? One thing that supports all of these particular cases, that's compatible with all these particular cases. Why is that? Well, it abstracts away from the how. And as a result, the person who creates the search function, for example, or this one at the bottom, has flexibility to substitute in a new implementation, right? So what I'm saying is, by parameterization, we can take many particular occurrences and turn them into reuse of one by parameterizing. Another thing we can do is take many particular instantiations of search and cover all of them with, any of them will be a legal implementation of this search. You might do the search in this way, you might maintain a heap data structure or a binary tree, or you maintain a hash table. All of those are fine. They might have some trade-offs performance-wise and so on, but they're all implementations of this search as described by this specification. And so the use of specifications, like the use of parameterization, allow us to take what would be totally different instances and cover them with one thing. In this case, this one description could legitimately describe any number of implementations of this. And that gives flexibility. Both of these give flexibility. Parameterization, we can pass different arguments, reuse it in different ways. Specification, we could substitute in different implementations of this. You get that? And we can substitute those in without breaking something over across the program, something that uses this. We don't have to worry that someone's counting on the gnarly details, right? They're not counting on the gory details. They should be counting on what's in the specification, what's promised here, what it does and not how. And you can be very clear with these specifications about what you can count on and what you can't. And that's really valuable because it allows the evolution of this component. Does that make sense as a general sort of situation? Just trying to cover points made last time but revisit them so they really sink in. Does that make sense? Okay, so now let's talk about this a little bit as it relates to the homework I gave you. So last time we had talked about refactoring of a program. What do I mean by refactoring? I gave you some crufty code, some really low quality code, and I had asked you to refactor it. What do I mean by that, by refactoring here?
Split it into functions.
Okay.
One example.
That's one example. What do I mean by refactoring as a general concept, as an abstract concept?
You could do the same thing, but more legibly.
It does the same thing. We haven't changed the functionality of it. We haven't changed what it does. We haven't changed its input-output relationship. We haven't changed basically what it accomplishes. What we've changed is just the details of how, and particularly we've improved some aspects of clarity, transparency, modifiability. We've made it more general, etc. This notion of refactoring is a very important one. You'll hear it a lot in industry because sometimes if you have a team that's delivering on, say, a staged incremental delivery process, maybe they'll take one entire cycle of 3 weeks and they'll just use that for refactoring sometimes. Rework the code, right? And often in the context of code, the first time we write the code, it isn't it doesn't, doesn't capture the best way to do it. So we often will go write some tests and make sure the tests fail initially. So you make it fail, and then you make it pass, and then you make it right. You actually do refactoring to sort of improve the quality of the code that you've created. Okay, so refactoring is a key skill in terms of improving code. And we went through that last time. We talked some about the code, but then I asked you to introduce some specifications in the form of, I suggested precondition, postcondition. So any comments on that exercise? I'll show you, as I am wont, one solution to this in a minute. Any comments on that exercise? Straightforward? Hard? What, were there parts of it that you weren't fully satisfied with, or which you found more difficult? Did the preconditions and postconditions, did they seem adequate for describing, together with a sort of overall description of the function? Did it seem adequate for capturing what was being done by those functions? Parlez-vous anglais? Yes, no, thumbs up, thumbs down. Okay. So some progress with it. What parts did you find the hardest? Oh, come on. You can come up with one statement, one utterance. Hopefully polite. Oh, come on. Was there anything hard about it? Or should I be looking for sterling implementations of it? Come on. Tell me one thing that was not trivial about it. Or was it trivial? How long did it take? Anyone want to volunteer?
Like an hour and a half.
Yeah. That's kind of what I found, between an hour and a half. Did it make you think at all about how to use preconditions and postconditions effectively? Okay. Anyone want to mention something about that you were thinking about? Like, was there something that you found unusually difficult with it?
Sometimes trying to find how to mention it without making it too specific for the program.
Good. Yeah, like to what degree should it be? To what degree should it really be tailored to the particular context in which it's being used? And to what degree are we just describing this function in isolation? So, okay, let's go look at this just to tie this down. Okay, here's this function, and I couldn't resist doing a little bit more refactoring with it here and there. I use bools more consistently rather than just saying ints for return values, etc. So for example, actually this wasn't caught by the compiler because we typedefed int to bool. What does this mean? This typedef, what does this mean?
You can use booleans as integers.
Yeah.
Have 1 and 0 for true.
That's right, and unfortunately the type machinery is not going to say, oh, there should be a bool, because it's considered equivalent. Okay, so here's some items with this. So I go through here and I provide a preconditions, postconditions for each element. I also did put in a little bit of support for command line arguments for the number of times to run it. I parameterized the program. Just like you parameterize functions, you can apply abstraction by parameterization at any number of levels. Here I parameterize the program, so it's not strictly a refactoring. I got the number of iterations based on command line arguments, or if it was blank, I used the default number. And I checked if it's not a meaningful thing, if someone passed something illegal, it will exit. Otherwise, it goes and reads these things in and runs it for this number of iterations. And I have preconditions, postconditions. And you'll notice that these preconditions and postconditions are not describing each one in isolation. So like argc, okay, I say it's greater than or equal to 1. Well, by the way, what's 1? And just remembering back to your C. What is the first one? Why is it always at least 1? Yes, it's the program's name itself, right. And then I say argv is of length argc. So this provides strings, however many as specified by argc. That's a criteria here, which is not immediately obvious from this declaration, but is involves consistency between these two, right? And and I described for post conditions depending on the command line, how many runs will it make, and then where the initial state is read from, etc. Okay. Okay, so let's go, and you could see there's some of these for each. Let's talk about a few aspects of this that I thought you might mention. First of all, each of these, and this relates to one of the comments back there, to what degree are we writing these in general, and to what degree are we writing them for the particular code? To what degree are they being tailored to the whole program context, and to what degree is it just the code? So, for example, read state here. Read state is reading in files, and we look to see the contents of those files to see if it's legitimate within our encoding. But at the same time, there's certain general criteria here. For example, we provide a file and we insist that it exists. So whoever calls this is responsible for guaranteeing that that file exists. Now, previously, and I'd like to use this for discussion, I had an assertion here for a couple items. And one of them, I think, involved the file doesn't end prematurely. One of them might have involved that the file was non-null. Why is that not appropriate to use an assertion? Anyone remember what assertions are used for? An assertion?
Validating assumption.
Validating assumptions. Validating their sanity checks. They validate programmer assumptions, the assumptions people use in writing that code. And so they're logical things. They're checking logical consistency. They should not be used to handle a case, for example, of a prematurely terminated file. Why not? Why not just say, I assume it's
That's a user issue.
It's a user issue. It's something that, as a programmer, you can't guarantee. Now, you could state it as a precondition that we assume that this file has these characteristics, is in this format, is of this certain length. In which case, legitimately, you could say then, for the sake of this file, I'm going to assume that. But absent that, you will not want to treat it as a simple assumption, but as a source for possible user error for which you will need to provide a comment back to the user. So specifications here provide a very important role in distinguishing and delineating for the coder who's writing this, for the programmer, what things can they legitimately count on. And you can push off to the people who call this file certain responsibilities, like testing, is the format of the file legitimate, if you want to do so. If you don't do that, you need to be able to handle errors, because you can't assume these things, and due to user error, the file might be incomplete, or it might be corrupted, or it might be unavailable on the disk, in which case you have to handle them as user errors. And it's not a bad idea to handle even assertions, things that you would normally assert as a user error if you're not sure other areas of the program will do so. So this was a little bit of decision making on my part. To what degree would I handle these as user errors? And to what degree would I handle them simply put up here in the preconditions the fact that this is not corrupt and that it is a full extent and that new lines end each row of the file, etc. So I chose to handle it as user errors with appropriate feedback for the user regarding the nature of the error. And probably I should have abstracted this. This to me looks ugly. You see all these different cases where basically it's the same basic deal. I issue a particular error message and I bomb out of there. I exit. And this could probably be abstracted out to one single function call, which issues an error and exits, although there's a bit of subtlety because these things print different information. Okay, so that was one thing. And in general, ladies and gentlemen, you have the luxury, if you write specifications, of saying what you depend on. You can choose to impose more things or fewer things in terms of the specification. So let's talk about that. In terms of what I'm counting on here, what are the trade-offs associated with it? In terms of putting in more preconditions, what are some of the advantages to that if you're writing this code? Having more strict preconditions. Why would you do that? What benefits does it offer?
Better narrow down what sort of information you'll be getting as input.
Okay. Can narrow down things and maybe simplify your life, right? Because you have greater clarity on, I can count on all these things, and therefore you don't have to handle as broad a set of possibilities. You know with confidence this thing is non-null, right? And you might, generally you wouldn't, but you might even put something in like, okay, there's memory free right now, at least 1,000 bytes of memory free, so I can allocate a certain structure. In which case you could assert, okay, the results of malloc of size 1,000 should not be null. Now what's the downside of putting extra requirements in there, in the preconditions? What's the downside of that?
Makes it more complicated to use your function.
Yeah, it makes it more of a pain to use it, right? People shop for libraries. They'll look, okay, what functions this library offer, this one, and it makes it more of a pain for users. What else? Why might that be a problem? If suppose you're in a team, and really it's being used by other people in the team. Why might it be a problem that it's a pain to use? Well, among other things, it might be most natural for certain checks to take place here. After all, if you required up front that this file is uncorrupted, that it's a full length, that all lines are terminated with end of new line characters, what burden does that impose on the person who calls this? Technically. Then they technically need to check that to make sure there's not a user error. In which case, there's another bunch of work, some function that has to validate that file elsewhere. And after all, we can validate these things quite easily as we're going through the file, just to read things in. So in some sense, it's more natural if it's part of this file rather than just requiring that it's a non-corrupt file. Because we have to, as mature programmers, we have to handle error conditions. It's not our foremost love, perhaps. Perhaps it's not what our heart rises to, but we got to do it. I mean, it's like, it's like basic hygiene and keeping your house in order. At some point, you gotta, if there's a rodent problem, you gotta make sure that rodents can't come into the house and so on. It's about being mature, and so it is with files. Things happen that are awkward. Things happen that are ugly, and you got to be able to handle them, whether they're being out of memory or things not being on disk or files are corrupt or the user gave this wrong input. You got to handle it. And sometimes it's most natural to handle it in your own code, like here. handling a file that doesn't exist or a file that's corrupt in some way. It has premature termination. It has illegal characters in it. It's most natural to handle it here. So you can push it off on someone, but then they have to go write other code to check it, and it's a pain for them to use. Okay, what's another disadvantage to you of promising more in terms of post conditions? Being quite particular about all the details in post conditions.
You can be too specific, and it won't. You can use a function in a way that you didn't intend to, but it won't be obvious from the post conditions.
Okay, so I like elements of what you're saying, Arlen. So one thing is you can be more specific than you need to. As a result, you tie your hands as to how you can modify that code, right? How you can take that code further, how you can evolve it. You tie yourself down in terms of the specifics, and therefore you don't have the luxury of refactoring it in a really general way, maybe in a way that allows you to use additional algorithms that are more efficient or what have you. So you want to be careful about what you promise as output as well in preconditions and postconditions. So in general, promising more, requiring more, they can have benefits, but they have costs. Requiring more, it make it easier perhaps for you to write the function. You don't have to, you can make more assumptions and deal with it, put aside some awkward cases. On the other hand, it pushes the burden to the user of the function. And that may be adverse, and it might not be a natural division. It might really require a lot of work elsewhere. With postconditions, you can promise less detail about what's ensured. You can promise more detail. Promising more detail may allow certain users who want certain features to count on it, but may limit your ability to evolve the function. Okay, so those are some comments on that. Let's talk about some other things, though. Preconditions and postconditions. Is there any place within this code where the preconditions have to do with things other than just the arguments to the function, like row and column? There's plenty of places with row and column, right? Here, the rows and columns have to be within certain bounds, for example, or time has to be greater than or equal to 0, or what have you. But are there cases where preconditions depend on things other than the arguments?
Global variables?
Global variables. So there are times where we count on global variables being around or having certain values or certain characteristics. An example would be this one right here. So run scenario. All I take is the count of steps in, but is that all it counts on? What else does it count on? Well, it counts on buffer even. Why? Well, we're just calling update space, and this is at time 0. So it's actually depending on the current contents. Whatever the current contents are, buffer even. When it calls off to update space, that's what it's counting on. And even that could be refined, because this is implicit here. I'm calling update space. Even this call doesn't pass buffer even. I just know that update space here, if you go down to that, it actually, if you go look at update space, this is going to call determined current and next cells, and this for time 0, it happens for the current cells to use buffer even. So I've got to be kind of careful here, because I've actually coupled this, and this assumption here, this is based on an understanding of how this function works, determine next to current cells, and the fact that, well, at time 0, it's going to be buffer even that goes into the pointer for current. Is pointed to by current cells, and therefore is the initial state. If this got changed so that we use buffer odd, or it was referring to another array, then this precondition up here, buffer even, is may actually have to change because it's merely implicit based on these other items. And because of that, I haven't done it here, and I probably should have. Because of that, ladies and gentlemen, sometimes the preconditions here have to refer to other functions. Let me give you an example down here. And it's down towards the bottom. You can look at this here. Okay, so cell value for textual encoding. So this takes in a character, and it basically returns an integer value that's used to encode that cell for the patch. It's basically the value to use for that patch in the long list of events. Now, you'll notice that the precondition here says C encoded is a legal cell value. That's a precondition. That's something we assume. And the way I specify that is I say, is legal textual encoding of C encoded is true. Now, this is legal textual encoding. That's just another function. So sometimes the preconditions for one function, or for that matter, the postconditions, might refer to other functions. This is very, very standard sort of stuff. That, in other words, to specify the preconditions, you specify them in terms of other functions. So here, in terms of the fact that whatever's passed in here needs to have a value returned as true if you pass it to is legal textual encoding. Does that make sense to you? Does that make sense? So the deal is preconditions and postconditions for functions are not necessarily written in isolation of other functions. They can refer to other functions to indicate consistency, to make sure that the functions are consistent with one another. And that's often really quite important. It's not merely that we describe each function in isolation as a fragmented thing, and that we describe this function and that one and that one, and we give specifications for each that are totally solitudes. In fact, the preconditions and postconditions we give to one function need to be consistent with the preconditions and postconditions for another, right? Another thing I could have said here, ladies and gentlemen, is the cell value for the textual encoding is really the opposite of another function. So there's functions that need to go both ways. So cell value for textual encoding here needs to be the opposite of one that gives the textual encoding for cell value, right? This one here. Do you see that? So for the postcondition for this guy, I could have written, I could have said guarantees that textual encoding for cell value, if you pass in this on a given C encoded here, this needs to be equal to what? The textual encoding. So if you give me a C encoded here, and I apply the cell value for textual encoding, I'm going to get back a 1 or a 0, say. I'm going to get back an int. And if I pass that to textual encoding, what do I need to get out? Something that's equal to what? C encoded. Exactly. Who said that? Your name? Alicia. Alicia. Thank you. So I need to get back C encoded. So in other words, these two are inverses of each other. Okay? They need to be consistent. So it goes beyond just describing each in isolation. There are some conditions that involve other functions and that refer to those other functions in the precondition and postcondition fruitfully. It could be that without a statement like this, you could have this legitimately to be described by the preconditions and postconditions, and similarly for this other one, for textual encoding for a cell value, but they don't play together nicely because they're not consistent, they're not compatible. One doesn't reverse the other. But here we want them to be inverses of each other. We want them to perform inverse mappings. So often our preconditions and postconditions, we need to capture things like that. Okay, so in short, writing preconditions and postconditions often requires not just one pass, but several passes, and it requires some thinking about what you're guaranteeing, how much you want to guarantee. If you don't guarantee it, who's going to? Is this the best place in the program to guarantee it? You are describing a given function, how it works in general, not just how it happens to be used in this program, but at the same time, you will sometimes want to state relationships between this function and other functions that indicate some sort of consistency that needs to be maintained between them. Does that make sense? Okay, so given that we have preconditions and postconditions, how could we use them in two things? How could we use them with assertions, and how can we use them with testing? So let's just go over that. So with assertions, this use of asserting, well, I'll say, assert this certain thing is true, is empty of a certain, item. What I'm I'm basically stating and I'm operationally checking a certain assumption on my part as the programmer. How could that make use of preconditions and postconditions? I'm not looking for anything mysterious here. Hopefully this should be fairly evident. How could I use assertions fruitfully with preconditions and postconditions? So you have these. You have these given to you, suppose.
Assertions should make sure that the preconditions are being followed.
Good. And for postconditions?
Assert that what you're handing out is valid.
Good. According to the postcondition, right? If the preconditions are met, the postconditions need to be met. How if the preconditions aren't met? Do the postconditions need to be met? No, you're not making any promises. Where you're making the promise is if the preconditions are met. It's in that case the postcondition applies. If the preconditions aren't met, the user shouldn't be counting on any particular behavior. It's kind of like the FedEx example, right? If you have to bring a package in by 10 a.m. to be in Ottawa by 5 p.m. the next day, and you don't bring it in by 10 a.m., we're not going to promise to have it in Ottawa necessarily. Now, it could be that you're just in luck. You bring it in at 10:30 and the truck to the airport is late and you can get it in there. But the postcondition that they normally guarantee is conditional. It's conditional on the preconditions being met. And you notice with the FedEx example that once again having a contract, an agreement in place that's abstract means you don't have to worry about all the details, who's behind the desk that day, the details of when the truck comes to the airport, whether it's being shipped on this flight or that flight. That's all hidden from you. All you care about is what it accomplishes. And it simplifies your life, right? Because you don't want to be thinking about all the flights out of the Saskatoon airport and which carry cargo and which are mostly passenger planes or what have you. Okay, so preconditions and postconditions form great uses of assertions. Now, do you think in assertions that you'll be able to efficiently check all postconditions? No. There may be some that are easy to check. For example, if you have the square root of a number, you might assert that whatever number is going to be returned, you square it, it should give the argument, right? So if you have a function square root, you're writing whatever it's going to return, if you square it, it should be, if you multiply it by itself, it should be the same as the argument. So in that sense, you might check, be able to check some postconditions easily. Others are harder to check. Others are more labor intensive to check. And therefore, checking postconditions is often not exhaustive. You might check some properties to make sure at least those properties hold, but you don't always put in a full check for the entirety of the postcondition. Or if you do, you might want to be able to disable it easily, even when other assertions are left enabled. Okay, so preconditions, postconditions provide a great opportunity for assertions. You check them, and you can find when they're violated, and you can find it early, close to the source often, because the first thing that you call, which has this violated, it indicates that. Note, ladies and gentlemen, that again, those preconditions, if you capture them in assertions, they may call other functions, right? So for example, in asserting for this guy here, cell value for textual encoding, you might call off for is legal textual encoding. You might call that function and ask, hey, is this legal? And when it comes time to ship it to the user, you might disable assertions in general, in which case that's not going to cost extra performance-wise, but it will check during testing that things are adequate. Does that make sense? Okay. So similarly, you might check this for your post condition. Check if that's the case. You call that in an assertion and see, okay, is it consistent? Does it jive? Are those things consistent? You might worry about performance, but assertions are normally disabled in shipping code. Again, there's some differences out there in industry, but very commonly they're disabled, and you should be able to disable them on a module by module basis as a basic component of many compilers. So here, don't worry about the performance side. Worry about your performance and finding errors as quickly as possible. Often that's going to bite the user more than hidden errors, rather than a bit of performance and assertions that are disabled and they never see the code with them. So you can check those things. Does that make sense? That you could check those in assertions, things like this? And this is very common once you start thinking through the consistency of the preconditions and postconditions as they apply to multiple things. It's not just each in isolation. There's relationships between the functions that need to be maintained. Another example would be read state, write state. Give me an example. What do I mean by it's related to this? So if I were to specify read state, write state, how could I, in what sense do they have to be consistent? Anyone? How could I write an assertion involving the read state and write state functions? I could describe each in isolation with preconditions and postconditions, but I'm going to miss an opportunity to check if they're consistent. What's one way I might check if they're consistent?
You read in what you write?
Yeah, you read in what you write. So if I have a given state, I should be able to write it out, read it into another buffer, and I should be able to check that those, the one that was read is consistent with the original one, right? That would check that they're playing with each other. Does that mean they're correct? Not necessarily, right? You could write out all nonsense characters and read always just reads in zeros, and so, no, excuse me, because I'd have to be able to take, for writing, I'd have to be able to take an arbitrary array. So it would be a little bit hard for you to write. So yeah, that's actually a fairly strong post condition, isn't it? A fairly strong guarantee that writing it out, that given an arbitrary, given any legal encoding with ones and zeros of a space, writing it out and reading it back in should yield the same space. There's actually a fair bit of, there's not a ton of wiggle room there. They need to be consistent with each other. It doesn't guarantee a specific encoding. It could be encoding with stars or with X's for where the cells are, but at least they need to play consistently and work together. So that's another example of something that you might check as part of an assertion in debug code, which is disabled in user code, of course. Okay, makes sense? Okay, now, assertions like this are provided, are specified in many different ways. The ones that I showed within the slides last time use a somewhat different convention. They use this thing effects. And in general, there's many ways of characterizing code here. So the effects here are describing something that is characterizing the post condition here, and it is providing a description of what it changes Often effects specify return values and then what has been updated or what has been changed. Sometimes closer to post conditions. But here you note that we haven't provided an explicit precondition clause. It's sort of packed up into this. And there's a conditional here. If this or this is null, then do this, otherwise returns true. So effects are one way to specify it. And in general, we can specify preconditions and postconditions, preconditions, effects. And we're soon going to see for object-oriented programming the use of history constraints and invariants. That's going to be coming later. Okay, and I noticed that there's different languages to support this. This is Eiffel. Used to be taught in this department. Quite nice language from certain perspectives. And you'll notice they have this requires clause, which serves as basically the preconditions, right? Under these conditions, this is ensured. In other words, these are the postconditions. And Eiffel provides that as part of the language. You'll notice, ladies and gentlemen, here, once again, this use of other methods here. Value for, has, etc., within the postconditions and within the preconditions here. And some of them are more mathematical in their formal specification. This is Splint. I actually contributed to the Splint project, which is a fairly popular, well-published system for doing preconditions and postconditions on C code. It makes use of comments to indicate what things are modified, so what things are affected, and preconditions here. And once again, you'll notice that they are using functions here. Okay, they're calling off to functions as part of their specification. Okay, so preconditions, postconditions are one way to specify it. Requires, ensures, preconditions, and effects clauses. We can specify these criteria in different ways. What is in common is we want to specify what we're counting on, and then if we can count on that, if that is met, what do we guarantee? And those guarantees sometimes involve return values, and they sometimes involve something else. Give me something else that this might involve beyond a return value. Anyone? If we consider something like update cell, I think would be an example, or update space. What might this depend on other than the return value itself? What other thing might be involved in?
The update cells function?
Yeah, okay, so update space returns a pointer to the latest state of the system. But what's also been changed is what? The content of that. So in other words, what's been performed here is not merely a return in a functional context. It's not merely returning a value, that's all it does. In fact, it's overwriting a certain buffer, right? It's overwriting a buffer as given by, as determined here for next cells. So it calls off to this, it gets next cells, and then it goes through and it overwrites that using update cell. So this buffer, whatever's returned here as part of next cells, the even or the odd buffer depending on the time, it will be in fact changed by this code. Why is that relevant? Why do we care? Why don't we just not care? Why do we care about more than the return value?
We need to make sure that buffer actually exists.
We need to make sure it exists. We need to make sure we're not counting on preserving it for other reasons. We've got things in there right now that we want to write out later. We need to have a sense of what this what this method does that goes beyond just what it happens to return. It needs to take into account what does it touch otherwise? What does it modify? What is it stomping on? That's also part of this. And if it's global variables, in this case that buffer, we need to know something about it. So it returns a pointer to the final state of the model, and it's encoded in the same in the same way. The final state was produced by running Conway's Game of Life for a certain number of steps, right? And excuse me. So this for a single step here, and that's and so therefore when we're considering the effects of this, we need to consider the fact that it stomps on one of the buffers, not merely that it returns a value. The same thing with update cell, as I think was mentioned earlier here. So here we return no value; it's void. But does this function have an effect? It's returning nothing. Does it have an effect? If we stripped out a call to this, would the program do the same thing? No. Why? What are its effects?
It changes current cells and next cells.
Yeah, it actually doesn't change current cells. It uses that, depends on that, but it updates next cells. And you'll see here it says the patch at row and column call in next cells is updated to hold the result. So we have modified something. In this case, it's not a global variable. In this case, it's pointed to by here. Now, ladies and gentlemen, this is not a small point. I mean, this issue of saying that what it modifies beyond the arguments is pretty important. If you're trying to puzzle over this code, knowing what this stomps on, what is this change, can be pretty valuable because it's not obvious from the name. It's not obvious from what you pass in as an argument what it does, that it's writing to these certain global variables. So having that as part of the specification, having that for part of the contract is pretty darn important, right? It's pretty important to have clarity. Also, this guy here, having a specification that next cells is actually output, it's actually being written to, not merely read from, that could be pretty important. You pass it in, a pointer to this thing, you think it's merely using it, maybe by its name, but it turns out that it's actually writing to it. Or if you're not sure which it's writing to, this makes it clear. So having that clarity on what is changed beyond the return value is very important. Very important. Does that make sense? Okay. Okay. So, ladies and gentlemen, that was part of this in terms of specifications. And we're going to come back to specifications just like abstraction by parameterization, back to abstraction by specification again and again and again. Okay, but I asked you to do something else for your take-home exercises. And what was that? What did I ask you to look at?
Make it more flexible so that you can change parameters easily.
Good. And change, well, okay, change, so that was part of it, parameters. I asked you to make it more flexible by allowing you to do what?
Implement more rules.
Yeah, to have different rules. How do we do that? Okay, so right now, let's look at this code. Right now, we have this code. We're running this scenario. The scenario is updating the space. Updating the space does update cell, and update cell calls compute liveness, and compute liveness is kind of where the action's at in terms of the core business logic, in terms of the core rule that updates the cell. All right? Basically, compute liveness determines, given the current state of the cell and the number of cells that are around it, does it stay alive or does it die? That's the core business logic. That's kind of the heart of the matter as far as the rule for Conway's Game of Life. Okay, so now we want to be able to have different rules here. How are we going to do that in C? Well, how are we going to do it even if you want to look beyond C? How would we do that? What do we need to do? So we want to have the same program be able to run sometimes with one rule, sometimes with another. And we'll leave it to main to determine which one to run with. How would we make it so it could run update cell with other rules? What could we do?
Abstract the value you measure against, like the number you measure against, and set it in main.
Okay, we might be able to do something like that, and we might be able to say, okay, we'll have maybe a global value that will say what's the minimum number to stay alive and the maximum number to stay alive, and we could set them up in main, and then we could, instead of comparing against 2 and 3, these magic numbers, these manifest constants, whatever number you want to use, or reference you want to use for it, we'll compare against global variables set up in main. Could we do that? Yeah, we could. Would that allow full generality in setting other rules? No, not unless we parameterized it also by something for this 3 here. But it would get us a certain distance, right? So I welcome that suggestion, Arlen's suggestion. That's one way you might accomplish that. Now, what would be, so it has some virtues, what would be a downside of doing it that way?
You're relying on global variables to be set.
Okay, good. And why are global variables problematic? Or why do they have to leave us pause at the least? Why are they problematic? Why do we try to stay away from them where possible?
Well, they could be changed at any time.
It could be changed at any time. It's not obvious where they change, right? After all, if we have clear functions, clear arguments, we can see what it depends on. But maybe secretly it's depending on this global variable. And of course, with specifications, that will be laid out, and that makes it a lot clearer. But still, it's a little bit obscure. Where is it used within the program? It's a lot clearer if we just say, it's up front and center. I call you with this information. That's all you need to do your job. The arguments, the formal parameters that I pass to you. That's all you need. It's clear what the contract is, right? I give you this, you give me back. If you're relying on global variables, it's not immediately clear, and at the least you need to have a good specification. Okay, so that's a good reason. And globals you have to be careful about. So global variables we need to be cautious about. It's not being, incredibly picayune and saying we never use global variables. You'll use them in certain contexts if it's fairly limited and so on. It's just you don't want to just go that direction automatically by impulse. So what's another way we could do it which would eschew global variables, that would actually avoid needing to declare any global variables at all?
Ask for a rule function.
Yeah, we could have a rule function. And what do we do with that rule function? So suppose we had a function whose job in life it was to compute liveness. Right? We could have, this is the standard compute liveness, and suppose we have different variants of this. One that allowed us to have between 2 and 4, or 1 and 4. Or, it had different rule for whether a cell's colonized. It could have between 2 and 3 for that. Suppose we had different functions like this. How could we tell update cell we want to use those different functions?
Pass it as a parameter.
Pass it as a parameter. I love it. You pass it as a parameter. You have it up, out in the open, straightforward. You want update cell to depend on it? You pass it as a parameter to update cell. Okay, that's great. So update cell is going to have a parameter that's going to tell what function to use for its update. And where would we use that function within update cell? So we're going to pass in a function that tells it how we're going to update it, what rule we're going to use for update. Where would we call that? Instead of what here? Sanity check? Yeah, instead of compute liveness, we'll call this function. Okay, okay, so if update cell takes that function in, what else do we need to parameterize to make it clean? If update cell needs to be given this function here, do we want to just specify what function to use here? No, we want main to specify it. So how is that going to happen? We need to parameterize what else? Update space. And update space is called from run scenario. So we need to parameterize run scenario. Okay, so how are we going to parameterize a function, all these functions, so that we give them a rule to apply? What are we going to give them in concrete terms? We're going to give them a... Okay, should I do it in slow motion? Okay, so, or should we play hangman? So it begins with P. The first word ends with R. There's a T here. Pointer, good. Pointer to a function. Okay, yeah, we're going to give it a pointer to a function. Now, what's that?
I said P threads.
Okay. Okay. Yes. Some relevance. Okay, no, we don't want to look at that. Okay, here we are. Okay, so I have done this. Here's main, and main is going to decide which rule to apply. And let's go down to the heart of the matter. Here's update cell. Update cell. This is where it used to call compute liveness, which really should say like is live or is become live. Okay, so here, what is this thing? What's this mysterious thing here? What are we doing? We're taking in a pointer to a function whose job in life is to compute liveness. Given two things, the number of current cells, if the current cell is alive and the count of cells around it, it's going to be able to do its job. So what is this thing here? Just a reminder of C syntax. Well, you folks should learn, if you're unsure about that, you should learn how to read something like this. What this says is, I'm passing in a thing called PFN, compute liveness, pointer to a function to compute liveness. And if I take that thing and I put a star in front of it and I call it and pass it these things, it returns a Boolean. That's how you read that, right? And that's a general rule for how you read things in C. You have this thing and you see, okay, what you apply to it in terms of the stars and the brackets, etc. And then you get out something. Okay, so this pointer to a function, compute liveness, I pass that in. I've given it a function. And what am I doing down here with that function? I am doing what with it? Well, what do you do with a function? You begins with a C. Call it. You call it. This is where it's being called, right? So whatever function I'm using, maybe right now it's the one that determines if the argument is between 2 and 3 and uses 3 here. Or maybe I pass it a function that determines if this is between 2 and 4 and counts if the number of surrounding alive is 2. Whatever function I give it, I call it here, and I get back an indication if the cell is alive or dead, 1 or 0. So I call it, right? Does that make sense? Are we on the same page? People feeling okay with that? So we're parameterizing this by a rule, by a function. We can pass in other rules here, and we will then update these cells according to other rules. And having done that, we pass it pretty routinely. This is standard stuff down from the top. So we pass from up here, we pass down to run scenario, we pass whichever one we want to use. Maybe we do compute liveness remain alive, or maybe we just say compute the standard, compute liveness 2 through 4, or maybe we do compute liveness 1 through 3, or maybe we do compute liveness whatever. Now, obviously, I could set it up so the user could specify in the command line which one they want to use or whatever. But the point here is that I have the flexibility now to pass in different rules from main down all these ways down to where it really matters, to where it's called. And now this is going to apply different rules here. This is the heart of the matter. This is where I was applying one rule earlier. And now we've made it flexible for applying different rules. Does that make sense? Are people okay with that? We've used parameterization to parameterize this by not just a number, not just the row to use or the column to use, but we've actually passed down a more general rule. And this rule could, in principle, use something totally different. It could roll a dice, right? It could ask, is the weather in Saskatoon today snowy? And it could set it accordingly, right? You might think those stars are cells, they're actually snowflakes. But the point is, it could use any number of different rules here. And we've abstracted that out. Now, update cell is not always for Conway's Game of Life. It now is by Conway's Game of Life or a variant, as specified by the cell mapping function, pfn compute liveness. So we have abstracted out what rule to apply. Are we clear about that? Now this is powerful. You saw it in operating systems class, evidently. Where else have you seen pointers to functions? I told you part of my job in this class is to fill in holes in the curriculum. Where else have you seen pointers to functions beyond 332 and 432 if you took it? Anywhere else? Do you feel comfortable with pointers to functions? Do you want me to talk more about this pointer to a function? Okay, so we've abstracted out the rule here by pointing a function. So we'll have different particular functions, right? This will be function 1, function 2. Each of these is a different rule for under what conditions it's live. Given the information that's available, the count, whether the current cell is alive and the number of cells, each of them will have a different rule for how to perform it. And main will say, this time use this one, or it'll say, this time use this one, and it will pass it down, right? We've abstracted out the rule. Now this is significant because the rule is something more than a number. It can actually be something very flexible. Okay, now this is going to get us to the next topic. So we've separated out this rule. How many of you have taken 340? Okay, a fair number. The ayes have it. That's good. So let me ask you this. How is this different from a higher order function in 340? A function that takes another function as an argument. Let's go to some slides, and we'll come back to this point. Okay. We're spanning a couple decks here. Okay. Before we get to that beauty, let's talk about these things. Okay. So suppose we have a two pieces of code here, sum and join. Does anyone see a certain amount of similarity between these? These are not in C anymore. What language is this? Anyone recognize it? Begins with a J.
JavaScript.
JavaScript. Good. Does does anyone see a certain amount of similarity between these?
Everything's the same except for 0 is now null character.
Okay.
Empty character.
Okay, so the 0 turned into an empty string, right? Joins together an array of strings. Sums up an array of numbers, right? Okay. Some similarity textually between these. How could we abstract over them? How could create one thing that sort of captures both of those? Anyone?
By passing in the parameter of what you want to save S as.
Good. So we could have the initial value of S, for example, and we just do that, yeah? Let's suppose I had another one, mult, that multiplies the elements of the array. So instead of plus equals, it is times equals. How could we handle all three then?
Pass in a function that contains the operation you're doing to S.
Pass in the function that contains the operation. In one case it's plus, another case it's concatenate, another case it is mult, right? And we need something, just as said earlier by, remind me your name?
Peggy.
Peggy. By Peggy, we want something for the initial value as well. Okay. So this is good. We have often pieces of code, and we can abstract over the particulars of the rule to apply. This is just like our case here. We've abstracted over the rule to apply by passing it a function here, right? So we often will have code that's pretty similar, and we want to pass in be able to pass in a rule, and basically everything else is the same. We just apply a different rule here. Okay. So how is this different than passing in a function in something like Haskell, or passing in a function in something like JavaScript, or passing in a function in something like Java 8 with lambda expressions? How is this different? How is a pointer to a function different? Okay, let's go to some later slides. Okay, so here's a function called map. Do you folks in 340 talk about map?
Mm-hmm.
Yeah? Okay. What did map do? What was map's job in life? What things did it need to do its job?
Needs an iterable list of something in a function.
Good. It has a collection of something. In this case, it's an array, or it could be a list, or whatever. It's some collection. And it needs a function. And what's its job? What does it do with those two things?
It applies the function to each element.
It applies the function to each element and returns
A new list.
a new collection of some sort. A list, or that has the function applied to each of those elements of the original list, right? Name?
Quentin.
Quentin. Thank you, Quentin. Here we have an implementation, sort of map in C. What's this thing here? This is a pointer to a function. And this is some, okay, I should have written it out. This is this is not C, excuse me. This is not C, it's kind of C-like. Okay, I'll rewrite it in C, okay, fine. And we create a new array, and we go through, and what are we doing in this step? Really, I should rewrite this in C syntax. I don't know what I was doing. So let me go call this up. What I need to do this in C syntax is do this, right? What this is saying is if I have this thing and I apply a star to it, and then I call it as shown by this thing around it, and I call it with these arguments, then I'll get back an int. And so I'm going to do this. So what is this doing here? What am I doing? I am applying the the function to the array, element of the array, right? And I'm getting back an array. Systematically, the new array, each element of the new array is the result of applying the function to the corresponding element of the source array, right? Right? And then I return the appropriate array. Okay, great. Love it. Love it. Okay, so this is an example of map. Now, how is this different than your original case? Eh? Okay, so this is map with pointers to functions. Now, here's the question. So how is this different? How is it different here? Let me ask you this, a very particular case. Okay, so here we're back to our code. Suppose we wanted perform liveness, this thing to compute liveness, this rule, to actually have a random number generator in it. It needs to maintain internally a random number generator to generate each successive random number. Maybe it applies the rule for most cases, but occasionally it throws a wild card and the cell is suddenly dead when it normally would have been living, or vice versa. Okay? So it has some randomness within it, and it needs to maintain an internal random number generator. So one of these functions that will be passed down by main, we want to have some random number generator inside of it to be maintained. How would we do that? If this function needed to maintain a random number generator internally, what could we do? So we want to write, we have these functions here, here's normal compute liveness, here's another one, and now we want to write one that maintains a random number generator. How are we going to do that? It's going to call off to a random number generator every time to generate a new number. How do we do that? Arlen's suggestion has some relevance, his earlier suggestion. How could we do that? So suppose we want to write a function, the morning is yet young, we want to go here and we'll copy all this, take advantage of the flexibility here. Okay, we're going to write compute liveness rand, okay, and we're going to have a random number generator, and we're going to basically take this, and 90% of the time we'll apply this, otherwise we'll return 0. And we'll have some randomness here. How would we do that? How would we maintain this random number generator? Where could it live? Could it live persistently inside of this function, so every time we have it? What would we normally do to capture this? So we want to have a random number generator here that's referred to. Okay, so here we have a random number generator, and each time we call it, it gives a new random number. So we need it to be persisting throughout all the simulation. Each time we call it, it gives a new one. Is it enough to just say random number generator here and then call off to it down here? Is this going to work? Is this going to work to have it declared here? That's uncertainty for you. Can we have it declared here? Will this work? We want to keep on calling it. It's going to give successive random numbers.
No, if it's inside the function, then every new time you call that function, it's going to restart.
Right. So, get new random number generator. I'm just, every time it's going to restart. That's not going to be any good. I mean, every time we call this, it's going to be getting the same random number generator and giving us the same value. We don't want that. We want to call it successively, asking it for successive random numbers. So what are our prospects here? What do we need to do in order to have this random number generator around so we can keep on calling it, getting new numbers? Where does it need to live? It needs to live globally. Globally. Was that Peggy? Great. So it needs to live globally here. can't live within this function. It needs to live somewhere else. It needs to live somewhere like here. And then we can call off to it here, right? And we could say if RNG, if the random number, maybe this is a pointer to a function. This is random number generator. Yeah, sure. I'll treat it as a pointer to a function. Okay, fine. We call off to it, and if it's greater than 0.1, then it will be true. Okay, fine. The point is, it needs to be global because we need to keep on calling it. Okay, we need to keep on requesting new numbers from it, and it's not enough that it lives here. So the question is, if we needed this function to have reference to values that it needs on an ongoing basis, not just each time it's called that are passed to it, but things it needs on an ongoing basis, those things have to be global. Those things have to be declared globally because they can't live within the function. Now I'm putting aside something called static variables here, but basically that's the deal in C. Statics are just kind of a nice way of achieving some global variables associated with this. And it turns out that we can do something much more effective with other languages that support functional programming. And we're going to see this next time. And it's called using closures. Closures, okay? Did you see this in 340, closures? Did you talk about closures? Yeah? And you talked about how you could create a closure, say, that would remember some value, and then every time you called it, it would say add a number to that value you had told about earlier, for example. Or you could create a closure that would associate a function with a random number generator. And it's kind of like that random number generator lives inside of that object, so it could keep on calling it without creating it new every time. Okay? So we're going to see next time how we can use closure to get around this issue. Not in C. C is our banged up pickup truck we just have to keep on using with all its limitations. But we're going to go next to JavaScript and use it as an example of how we can create closures in a more functional style. And we will see that will allow considerable extra strength beyond what we can do with pointers to functions. Okay, so that's all for this time. I'm planning to post a small take-home exercise at most for Thursday to keep the work light during the week. But I'll see you Thursday, and we'll continue a discussion of functional abstraction. Thank you.